All right. Sorry about a little bit because I haven't taught online like this for quite some times. Okay. Okay. So today we're going to continue on chapter 7, which is more detail about how to design the digital system based on the HDL examples, and want you to visualize how we can design any digital system and how we can start off. All right. Okay. Yeah. First of all, let's review what we already know. Okay. Let me add one more square paper. Okay. Okay. So in computer system or digital system, actually you can view the component of computer into 4 components, right? Yeah, we have talked about that in 206. I don't know if you still remember that. We have 4 components, right? We have I/O components, input components, right? And then we have ALU, and then we have memories, and we have O or output. Or this block sometimes we just call I/O. Okay? And then we see that we can see the movement of data or the actual number that we are working on between these 4, right? Okay. And with the control in between, so this is the control unit. Okay. With these things as the control signals. So we can divide it, this thing into this, right? So the blue lines usually is called the data part, where the actual data or number that we want to work on is flowing through all this part, right? And then the green one, this is what we call the control part. Control part. Okay, or control signals, same thing. Okay. Then we can have output, input and output from outside. So this external data. We can import external data, okay, and we can also export or output to external entities, right, or next unit. Okay, sorry. Or you can say external devices to the other devices. Okay, so these are basic components in any computer system. Okay. Anyway, as you can see, in any digital design, so it consists of these things. But the examples that we're going to show you today is going to be some simple stuff, because these are most common in CPU, right? And do you still remember the CPU? So the CPU include what? The CPU include this, right? Mostly, and part of this, most of the times, where this part is usually what we call the cache or small memories within the CPU. Okay, and actually today's it's also include this part as well, the I/O interface, where you can talk to outside. Okay, so and this can happen because of Moore's law, because now you have more space or more area, so you can include more and more components. But of course, it's not going to be the best I/O, but it helps you in working faster instead of just separate into different chip. Okay, right. First of all, before we start doing anything, what is the first step that we're gonna do if you want to design, let's say, a product, digital product or something like that? So what is the first step that we're gonna do? Okay, I make you a choice. Okay, first, are you going to pay interest to the hardware to be used? Or two, you're going to pay interest to the software to be used? Or the third one, will you concern about the algorithm use? Right? Algorithms mean what? The sequence of events or steps that you're going to work on. So we call algorithms. And number four, this is the user manuals. Okay. So what do you think? Which one we gonna make first? Huh?
Algorithms, sequence of steps, just to get a like overall, idea of how it is supposed to work.
Oh, okay. Now, your friends here online tell me that we should consider algorithm first. Okay, but your friends in the room say that the user manual should come first. What's your reasons? Okay. Yeah. Okay. Actually, the most important step is number four. Actually, when you want to design anything, it's quite counterintuitive, right? So basically, you imagine first how the people gonna use your products first, okay, or how your kind of products will look like. Because have you learned what's called the exploring? No, you guys have your own exploring class, right? But what is the first things that they taught you? You have to do what? Empathy work, right? So are you familiar with this word? Empathy work, right? Actually, you want to find the requirements that the user needs, right? And this will be translated into what? It will be translated into what we call the features or function or functionality, right? Functionality, okay. That will define your products basically. And that's why some of the products like will be a failure once it's released. Why? Because you never consider the feelings of the people, right? So when you want to sell something, it will collect the dust because nobody wants it. Okay, and so we want to produce some things that people need. So if people need it, then they will buy it, right? One of the example that I told you before is Apple smartphone, the first one, right? Before that, they have like all the Nokia's, the Blackberries, the one that has the whole keyboard on the phone, which is very small. Sometimes you have to use the joystick or the sticks to press the keys, which is very inconvenient, right? And so the the first people that noticed this is who? Do you know who? Steve Jobs. He figuring out that nobody's want to use like this kind of stuff, right? So he knows that people want to use minimums, pushing stuff. So he figuring out that okay, my smartphone will require just one button. So he get rid of all buttons, right? And then what happened next? Because you don't have any buttons, then how you solve the problems of how to type, right? And here's come the touch screens, so you can show the keyboard on the screen and let people touch it. But the point is that the technology hasn't advanced enough at that time, right? So he looks for the company that can work on this, and he found a company in I think in Korea that that almost did what he wanted. So he chased after that companies until they get what he wants, and that's when the first iPhone come out. And what happened? Everyone want iPhone, first iPhone. And what happened to BlackBerry? They went bankrupt because nobody's want to use them anymore, right? Okay, and that what's one of the clear examples in technology. Okay, Yeah, okay, but another dimension that you also have to consider, and that will be actually the choice of other stuff. Once you can determine the features of functionalities, those will determine what will determine the algorithms that you use. For example, if you want these features, what can the products that can do, and what step that you're going to use. You see, in the user manual, usually you will tell what. For example, if you want to dial some things, you press this one and this thing will pop up, and then you click this and that's pop up. So you actually have the steps of doing some things on your products, and that will define the algorithms in general, right? And this algorithm can be like break down into a small piece of algorithms, for example, like multiplication or whatever. And these algorithms will determine the hardware and the software that you use. Of course, the hardware will also determine the software that you're going to use too, right? Because depend on how complex the software, the hardware is, right? Then the software need to control the hardware, okay? And that will also complicate stuff, okay? And all of this actually under something that we call what? This is, okay, cost. You still have to consider the cost, right? Because sometimes the option that people want, of course, will be, you can do it, but it's going to be expensive. And if it's too expensive, then nobody's going to buy it, no matter how good they are, right? But if, you know, except that you show off some things, but it's not gonna stick around, okay? All right. So actually, this is how to work backward, right? The hardware to be used depends on the choice of the algorithms that you use, and the algorithms will determine the hardware that you use. That's one thing that I want to show you, okay? Then after that, then we can building from number 1 back to number 4, right? This is how we construct it, okay? But of course, the first one is the empathy work or working out the requirements. Okay? So this is more or less like a top-down approach, okay? Let's see, let's assume that, so we know the algorithm to be used and we determine the hardware to be used. Then how are we going to write the software to control this? Okay, let's show you an example. For example, this one is a simple digital system where it's constructed, has just a number of registers. You know, you remember what the register is, right? It's a collection of flip-flops, right, to store the result or the digital data, okay, until you want to use it, of course. It's an array of some things, and of course there are so many variations. You have what PIPO, power in, power out, zero in, power out, or whatever. But these are simple registers. Okay. Here you can see the blue one, the blue bus, right? The blue bus here. So this is what we call the data bus, right? This is where the actual numbers flowing. Okay, going from one places to the other places, okay? And then the black one is what? The data part. It is the control signal. Okay, so what is the data part? The data bus or the data path? This is what? The actual number, right? The actual number or data, actual numbers or data to be computed. Okay, and the control signal is just to what? To control the flow. Control signal means control the flow of data from one point to the other point. Okay, and also you can say synchronize, or you can say what? Orchestrate, right? Orchestrate the sequence or the things that happen, orchestrate all these events. Okay, so these are what we call the control signals. Okay, so you can see the control signal doesn't change anything, right? It just redirect or reroute the data from one place to the other place. Okay, and the actual data has been computed somewhere. For example, in adders, in multipliers, or whatever that we design. Okay, but here in this example, just a simple one where you just have a number of registers and the control circuits. Okay, and of course, to do this, as you can see, the bus, right? Do you remember what the bus is? The bus? It's not the public bus. The bus is the path, right? The collection of signals or path that flowing in the same direction. So basically, it carries what? It carries a group of data that has a meaning. For example, it can be a code, right? It can be a number, binary number. It can be anything, right? That collected together, then we call the bus. Of course, nowadays you can have what? 8 bits, right? 16 bits. Nowadays what? 64 bits, right? In the CPU, most of the CPUs. So it depends on what do you want. Of course, the bigger the bus or the path, then the more resource you're going to need for that. Okay, for this simple system, you have, for example, up to K registers. Okay, and then you can have the control circuits. So what does the control circuits do? Of course, you have to determine what you can do in the digital system, like I said before. So you start off with this, right? And then you work backward. Okay, so basically it's depend on the job, right? So this is the job that you want to do. What kind of job that you want to do, okay? And that will determine the hardware use, okay? For example, this is a very simple one. So what it does is it just shifted, okay, the data around from one places to the other places. For example, you can shift the data from R1 to R2, for example, or you can swap R1 with R2. That it can be done. Move data from one register to the other register, or swap the data from one register with the other registers. Okay, so that is the jobs that this digital system can do, and it cannot do anything more than that. Okay, and that's it is. Okay, and this comes from the requirements. Of course, if it can be done, then the complexity of this will go up, of course. Okay, and you can see this simple algorithms is this. Okay, for example, let's assume that we limited ourselves to just 3 registers. Okay, let's say this is R3. You have just 3 registers. Okay, and so this will become RK in will become R2, and R will become R out. Okay. So what it does is it can be done like this. Okay. For example, if I want to swap, okay, the job is to swap. Yeah, let's work on this. Okay, the job is to swap R1 with R2. Or you can say R1, R2. Use symbol like this. You can swap. Okay, so that's the command. We call command. Okay, let's move swap R1 with R2, right? Okay, then what is the level 2? Level 2 is what? You have to figure out the algorithms, right? So that's the job. Okay, then the second level is the algorithm. What is the algorithm then? Can you just move R1 to R2? You can't, right? Because what? Because you have just one bus, okay? And one bus, if you are not careful, then you can lose what the data inside. Okay, yeah, let me explain this a bit. You understand what are these things, right? You still remember what are these? We call this what? Tri-state buffer. Still remember what it is? Still remember what it is? Okay, A tri-state buffer is the control or the gated buffer. What is a buffer? A buffer is simply just a driver. We use buffer to what? To boost the capability of driving the signals. Okay. Yeah, let's try this. Okay, so what is a buffer? Okay, normally you can just construct this one right away. I don't know if you still remember. For example, if you have a gate and then you can drive the output F, A, and B directly, right? Okay. However, if this point is actually driving a lot of gates, another gate, then this gate may not good enough to drive all this point because it doesn't have enough power to drive all of them. Okay. So we can boost it by just using what we call the buffer, right? For the buffer. Yeah. And this buffer can, of course, can what we call the fan out, can drive more gates. So this is can do it, right? This can, but this is okay. We use the buffer to do it. Okay, so the logic is actually the same. For example, if this is D and this is F, of course, F equal D, right? But the difference is that it can drive or give out more current than just one gate. So it's a specially designed circuits that can do this. Okay, so we call buffer, right? Okay, but what is a tri-state buffer? The tri-state buffer is simply a buffer followed by, you can see a gate, right? Gate. You already learned this, right? If I remember, right? Okay, and this is controlled by what we call the control signals. This is the control. Okay, we usually call S. Okay, on the tri-state buffer. So this is A, this is B, and of course the state. So there are three states now. Depend on S. If S is 0, then what is B? B is high impedance, or you can say that it's flooded. It looks like you have a switch, right? And this switch is open. So what is the values of B? You can say what is that? It's just like a wire that floated in space. This is space, right? It's not connected to anything. It's like an antenna that floats in the air. So basically, it will be deducted into the voltage that it's connected. So if you connect 5 volts, then B is 5 volts. If you connect to 2 volts, then B is 2 volts, right? But if you have nothing there, B is something like noise. It will pick up noise from the air, right? And B will just the noise. So we call this state the high impedance state. It looks like you have a very big R that flowing to the air between the air and the ground. So that's why we call high impedance. Okay, but if S is 1, what happened? If S is 1, then this is closed, right? This is closed. And then B equal A. Okay, because A will be connected to A. Logically, right? But electrically is different because then B much stronger than A. So you can drive lots of stuff. Okay. And what does this mean? Means that you have the control signal external. So if and remember that we can have many type of control depending on logic. This is active high logic, right? Because when the control is 1, then you expected something to happen, which means that you connected B to A. Okay, so we call this the active high. But if it's active low, then the symbol will be this, right? With the control, we have a bubble on it. We'll put a bubble on here. Okay, or we can put the bubble on the outside here too. Then this becomes the inverter, right? Buffer inverter. Yeah, depends. Okay, and yeah, these are symbols that you may see very often in these digital circuits. Okay, so what are the details of this? So what does it mean? Okay, yeah. When you see all these things, you should be able to visualize what does it mean. For example, like this, the bus is had. Let's assume that this is 8-bit. Usually, they will give you a slash with a number here, which means that this bus is 8 bits wide. Okay, it's wide, which means that these things will have 8 number of bits. Okay, let's say it's 4 for simplicity. So what is you see here? This is something like this, right? 1, 2, 3, 4. With the command control, or these are connected. Let's draw this. So these are control. What we call control. Yeah, you can see that, right? And the output here. Because these are 4-bit, let's assume that the bus is B, okay? And so you have 4 bus, right? Let's draw bus. So that's a bus. 1, 2, 3, 4. Let's assume this is 4-bit as well. Okay, so this is B. Let's say B3, B2, B1, and B0. Okay, so these are connected to this, right? B3 is connected to this. So that's the meaning of it. Okay. Oh, okay. So this is sorry. Oops. These are not connected like this. Sorry, not this way. It's this side, right? This side will go up to 1, 2, 3, 4. So it's connected to 4 lines here. B3, B2, B1, and B0. That's the meaning of this one. Okay, and where's the other one goes? It's go to R1 and R2, right? And remember, R1 is actually consists of 4 registers as well, because everything is 4, right? We call it the data path width is 4, which means that the register has to match the bus. Okay, so this means that you also have 4 flip-flop. Okay. 4 flip-flop, and this flip-flop from the registers R1. You have 4D flip-flop. Okay, and these come from this side, right? And this go back to the bus. So those are the details. Okay, so this go back to the details here. Right? I'm wrong, sorry. It has to connect the right one too. This one back to this, right? Because B0 has to connect to B0, so it's come down here. So you can see that it has to match correctly. Okay. So that's D0, D1, D2, and D3. Okay. And these are common clock, right? So the clock go instead. Okay. So you need to understand the details, because if you don't understand this, then when you actually implement it, either in hardware or using the VHDL, you should be able to clarify all this, or else you're going to confuse yourself and mess up when you want to actually design. Okay, any questions? Understand which ones go where? Okay, and these things we call the command control. For example, when this is going in, it's going to all the flip-flop. For example, you have you have this one, right? I1. So where is I1 goes? I1's go here, go here, go here, go here, and they're all connected to be the one signals that going into R1. Sorry. Okay, so it's command control. We call this type of features is command control, where the control the redirection of everything into the same way or the same manners. Okay, sometimes it's not. So, but most of the times it will be command control. Okay, except that in some cases it's not, but mostly that's why you should be able to at least identify it. Okay. Yeah. Okay. So these are the details that you should be able to sketch at least. Yeah, you never know. I may ask you how to sketch this part. So how it looks like. I can ask you too, if you understand, what's the actual meanings of the schematics that you have. Okay. Okay. Yeah, let's come back here. The first one, of course, the first level is the job. Let's say that I want to assume R1 and R2, or you can say that sometimes we just call this command, right? Command that you want to do. Okay. Then you have to figure out for each command of each job what the algorithm is. Okay. If you see R1 and R2, can you swap it directly with this hardware, under this hardware? Okay. Yeah. Under this hardware. What does it mean under this hardware? Of course, if the structure of the system is different, then the algorithm that you use will be different too. Okay, so everything is the same. But anyway, if you consider algorithm first, so what we're going to do, if you want to swap two numbers, okay, let's assume that if you want to try moving R1 to R2 first, what happened? What happened if you do this? If you want to swap two numbers, R1 and R2, what happened? R2 will be disappear. You can't get it because it's overridden by R1, right? So it's not that simple that, R1 to R2 and R2 to R1. Can you do that? No. So what do you need to do? What do you need to do? Huh?
Save it in an arbitrary bit first.
Yeah. Okay. So assume that if you have just three registers, so what do? You have to move R2 to somewhere else, right? Or R1 to something else first before you can start doing some things instead. Okay. Then what? R1 to you have to move up R2 to R3, right? Then what? R1 to R2, right? And then what? R3 to R1. So basically you need extra registers to do this. You cannot just do two registers. Okay. So that's the algorithm that you need to do. And you can see that we actually have to think of the sequence that happened. So it's going to happen in 3 steps. You cannot do it in just 2 steps, right? And it's going to involve another extra registers, for example. Okay. Yeah. And number 3, like I said before, is the hardware that you pick. So it's all related, the hardware that to be used. Okay. And then number 4, the software. Of course, this is going to be related to the software. Because you pick this hardware, then you have to generate the software, which means the algorithms or the sequence that this happened. You have to generate the signals or the controls to do this. Okay, and this is going to happen in 3 steps. So you need 3 sequence of signals to do this for each step. You have to control each step in sequence. You cannot just jump. For the first step, what is the first step? The first step is what? Release R2, then store R3, for example, right? The first step is to release R2, the data from R2, and then R3 have to accept it. Okay, so you need 2 signals. One signal is to signal R2 to release the signal. Okay, and then another signal to tell R3, hey, to receive the signals. Okay, so you need 2 signals. And then the next step or the next sequence is what? Release R1, right? Release R1, and then R2 receive it. Okay, and then the first step, the third step is what? This R3 and then R1. Do it. Okay, so that's That's what happened, right? That's what happened. Okay. Let's see if I correctly do it. Yeah, okay. So as you can see, the first step is what? Release R2, and then R3 have to release it. And if you consider from the hardware, you can see that how can you release the signal from R1? Of course, you open the gate by controlling R1 out, right? No, not, sorry. The first step is R2 to R3, right? R2 to R3. So you need R2 out first. You have to control this one to be active, R2 out active. That's the first step, right? To what? To release R2 onto the bus. And then from this R2, it's going to be expand or extended in both directions until it's form a stable output at all the gates, right? The data is like, at the gate of each registers, but only one will be accepted, right? And that exception is come from do this. So you activate this as well, right? So this has to be one, and this has to be one, right? The first to tell R2 to release the output, right? And the second one to tell R3, this has to be 3, sorry, R3 to accept it by enable the registers to let the data go in, okay, right? And then what? And then wait for the clock. Okay, so for each step, you can see for number 1, R2 to R3, still you need 2 sub-steps. Actually, the first one is to what? Activate, or you can say R2 out equal 1, right? And R3 in equal 1, right? To activate. This is release R2, right? And this is accept by R3. And then what? And then wait. Next step, 1.2 is wait. Wait for what? You have to give the clock, right? And what is the type of clock that you're looking for? Of course, this is going to be what? By looking at this signal, the rising or falling edge. Still remember?
Rising?
Yeah, it's a rising edge, right? So you have to give a rising edge to what? To let that happen, right? Because the data is released, but R3 can store it only when the clock edge comes. And that clock edge is the rising edge, because you can see from the symbols, this is your choice. You want the falling edges, you just push the bubble there, right? Okay, but here, for this particular example, you decided to use the rising edge. So you have to wait, okay? And that's the first step, okay? And then what? The second step is R1 to R2, right? And then we're going to repeat R1 out equal 1, right? And R2 in equal 1, okay? And then wait for this. Okay, and then the third step, R3 to R1. So that's what? R3 out, right? And R1 in equal 1. And the others is 0, right? Yeah, and wait for this. So it has to move in 3 clock cycles. You can see that. This command, this job, you require 3 cycles. 3 cycles of rising edge in time. The first one is move R2 to R3, right? The second one will move R3 to R1 to R2, and the third step will move R2 to R3. R3 to R1. Okay. So you see, each command, each job can take several clock cycles, depend on the algorithms that you use, right? And this, of course, depends on how you design the hardware too. Because if you have different hardware, then this step will be different. Okay, will be different. Okay, and Okay, so you see the sequence that happened. So what we do is we can design a simple one using the control one. So what are these blocks? This block is this block, the control circuits. Okay, so these are the control circuit. This part that is in slide 4, number 4. This is the control that we talk about, control circuits. Control circuits. Okay, for 3 registers. Of course, if you have more registers, then it's going to be more signals, and of course, the control signal is going to be more complicated. The more job that you put on, in what function that you can do. Okay, for this particular example, the only function that this can do is to move or swap to registers. Okay, and here you can see that we can determine this. If you write this one out, the signal out, you can see that if you write the signal out, of course, it's have 1 in, 1 out, right? And then 2 in, 2 out, 3 in, 3 out. You can see the sequence that happened. So these are all 0, the first step, right? Except R2 out is 1 and R3 in is 1. Okay, that's the first step. Okay, the second step, when each edge, this is for each edges. Okay, the second edges is going to be what? 0, right? 1, 1, and 0, 0, 0. And then at the third step, it's going to be 1, 0, 0, 0, 0, 1. Okay, so you can see the first clock cycles that happen, the first edge, you have to generate these 2, right? But it can be easy because this one, we can accept it from outside. For example, if you want to do this, you have to signal to start the command, and that's come from the W. W's been, you can say swap, you can say start swapping, something like that. Once it's read this, it will generate. So if you don't do anything, W will be equal to 0 initially. Okay, but when you signal that, oh, I want to swap, then W will become 1. Okay, and once it become 1, and then the clock cycles come in, as you can see, the first, when you start it, after the first clock cycle, this will become 1 and 1, right? Because this go to 2 signals, it split it into 2 signals, and these 2 goes there, right? Goes there. The first one, right? The first signal is these things, right? R2 and R3, right? That's the first step. Remember that we generate this signal, so it's go there. Okay, and the other signal is going to be 0. Okay, because you don't do anything, it's going to be 0. Okay, and then again, these 2 signals will generate. Then the next signals, because it's the same, it's like a wave. You can see that it's like a wave. So you don't do anything complicated. You tie this together, right, and move here. Move here. That's what we do. So we shift it. We shift 1 at a time. The first one that we generated, we send it out to R2 and R3 in. And the first, and once you shift it, then it's going to go there. Right? It's going to go there. When W is 0, then everything will be 0 because it's going to get shifted by the clock. That's before you start doing, right? But when you swap, as you can see, W will be equal to 1, and this one will be propagate 1 by 1, 1 by 1. Of course, you have to withdraw it after the first clock cycles when you start, because it's going to be and go back to 0 after the clock cycle. So the 1 will be like waving through all this stuff. Okay, so the first clock cycle, it will be 1, 1, and then this one will be moved here, right? And then move here on the next cycle. So you can see the wave actually. Okay, so yeah, I think this is the difficulty of digital circuits. You have to visualize what happened, right? Because there's nothing that you can compute it, right? If you understand it, you understand. If you don't, then you don't. So maybe you have to spend some time to figuring out. So most of them are like algorithms, like to think what action, and that action can be controlled or generated by what. And these are the simple stuff. Okay. Of course, there's more complicated stuff. You can think about the logic. You can create a big logic that compute that, oh, I'm going to generate this to 1 at this particular time. Of course, it's going to be some combinational logic. Of course, you can do that too, okay, by designing objects. Okay, but these are simple stuff. So you can use shift registers. So these are basically what we call the shift registers, right? We just shift the one that happened here, go to times, 3 times. And each one that we shift, we use it to control the sequence or the actual signals that need to be 1, right? It's easy because you see that we actually like go through the steps and waving, okay? So it's like a simple stuff. So we can do this. Okay, and here is the control circuits that can be used for this particular job. Swapping these 2 registers, right? And also with this hardware. Okay, but if you change the hardware, of course, you will change the control circuits, right? The way that you want to control these signals, you can change it. Okay. For examples, let's say this example first. Okay, the alternative to the buffer, the tri-step buffer, is to use a bus, right? Because of what? Because all of this, as you can see, the output of each register is actually feedback to the bus, right? Or you can say that the bus can be accessed by 1 register at a time, right? 1 register at a time. So basically, it's the sense of choosing something. For example, if you have 3 registers, then you choose one of them, right, to access the bus. And that meaning is a multiplexer, right? Give you a sense of multiplexers. For example, if you have 4 registers, but this 4 register can access bus 1 at a time. So basically, you pick 1 from 4, right? So that is a max mentality. You can say that. Okay. So basically, instead of using the tri-state bus, you can use multiplexer. Okay, you can multiplexer. For example, if you have K, let's say 4 bus, for example, then you need what? What's the size of the max? What is the size of the max? If you have 4 register, what the size of the max is? Okay, there are 2 numbers here. One is the width, the part of the width of the data part, right? And the one is what? The groups that you want to swap. So how many groups? 4 groups. So you actually need what? 4 to 1 max. This is 4 to 1 max. Okay, but each max has what? 8 bits wide, right? 8 bits wide, right? 8 bits. 8 bits wide. So what does it look like in this case? So what does this one look like? What does this one look like? Okay, let me draw something. Okay, so what does this one look like? Of course, the control signal, how many of them? If you have 4. 1. So basically what we say is you have 4 ports. 4 ports. Port 1, port 2, port 0, 1, 2, 3. So what is 4 to 1 max, right? So you need what? 2 control signals and give out 1 port here. So this is S2, S1 and S2. You need 2 signals, 2 control signals. Okay, so what does it look like? You need 4 to 1, right? So basically you have 4 to 1 marks. These are 4 bits. Each bits go in here. So you pick up what? You pick up the first bit of each part, right? For example, P0, 0, that's the first bit. Then P1, 0, the same significant bit, because as you can see, P0 is, you have 4 bit, right? So it's P0, 0, P0, 1, P0, 2, right? And P0, 3, right? And this one also have 4 bits. It's going to be P1 bit 0, P1 bit 1, P1 bit 2, and P1 bit 3, right? And so what is the max? The max P0 has to be multiplexed with bit 0. Only bit 0 multiplexed together, right? So that's why you have this 3 bit 0 and came out as what? Let's say this is the bus, right? Bus 0. Okay, and then bit 1, this bit 1. Then go out to bus bit 1. Okay, and same here, that's bit 2 of every bit 3 of every things, and then come out. Okay, so that's the meaning of this. Okay, the shorthand of this. Because if you write out the detail, it's going to look like this and it will be quite messy. Okay, so we call this level RTL level or register transfer level. So it's quite different from the bit level. Yes. Sorry? Yeah, we assume that it's 4 bit. This one, go back to data bus. Yeah, it's the same bus. As you can see here, this is the same, right? The same. When it came out, it's go back to the bus. Everyone's go back to the bus. Yeah. Yeah, that's right. What do you mean 5? No. This came out. It's, you can see that the data flow in one way only. Always flow in this direction, right? But here, maybe not. The bus can be flowing in both directions. For example, if you want to move from R3 to R1, when it's released, that R3 go moving this way, data moving this way. But if you want to swap R1 with R3, the data will move this way. Different. It's bidirectional bus. Meanwhile, this one is one directional bus. See that? It's always flow this way. Okay. Yeah, and of course there's advantage and disadvantage of both things. Okay, let me discuss that later on. But for here, do you understand, right? The meanings. So these are what we call the RTL level, but this is the bit level. So it's RTL level design and bit level design. So that's the meaning of why is the difference. Okay, and as you can see, for marks, of course, there's no collision. Why is there's no collisions? There's no collision because each one can access the bus one at a time. The marks will determine that, right? Determine that. Why the one that use the tri-state bus, you can see that everyone can access the bus, but you control who will access it. What happens if you if you control these 2 buses and activate at the same time? So what happens? Well, the data will be released from 2 of them, right? And then what? It can be collided on the bus, right? So it's like come out crashing. So you don't know what it is. You remember that these are like some things that you should never do, right? What happened? Because one of the registers is going to be damaged, right? pretty much. Do you remember that for output, you cannot connect them together, right? For example, like this. What happened? If you connected the output together directly, what happened? If there's conflict between the output of each one, then one gate will be destroyed for sure. For example, if this one is 0 and this one is 1, the output of this one will be 1, right? And the output here will be 0. But then what is F? Then what is F? Do you remember? Of course, 1 is 5 volts and 0 is 0 volts. What happened? One gate's gonna give up for sure, right? So never do this, right? But for tri-state buffer, of course, you can do that. Because you control the gates. Remember that? Because these are right, like you can control the gates, right? Because it's something like this. Right? As long as you don't close the switch both at the same times, then you don't have problems. Unless you close them together and there is a conflict in the logic, then it's the same situation as this. So it's your, what do you call it, your responsibility to control, to make sure that there's no collisions, right? Okay. This one? Yeah. Yeah. No. That's why they have the data, because it's flow one way, right? This one sometimes, yeah, you can see the data. This is flow one way as well, right? But it's going in here. It's always flow in, but on the bus, it can flow in both directions on the bus, right? But it's always going resistors, okay? And it's always what we call distributed or extended to all the resistors. But here you can see that one at a time, but of course, it's different. Okay, so what are the advantage and disadvantage? What do you think? What do you think? Huh? Okay, what's the advantage of this? There will be no collision for sure, right? Because everything is determined by mass. There will always be just one to be able to access the bus, right? There will be no collision. Okay, but what's the disadvantage? The max is huge. This is a gate. Remember that? How you gonna design the max? 2-to-1 max. How many gates you need? You need 4 gates at least for the max. Okay, so in terms of hardware, likewise, this architecture is much smaller. Like much smaller, because it's just a gate, like just a buffer, which is quite small compared with max. And you can see that how many max you need. There's a lot of max. Depends on the size, right? And also the bit number. For example, if it's 8-bit, then you need 8 max. But why in a buffer situation, you just extend it with 8 buffers, which is minimum. Okay, but of course, there will be collisions if you don't control it well. Okay. But what do you think? In most CPU, what kind of architecture that they want to use? They usually use these architectures. Why? Because it's smaller. You don't have that much space on the CPU. Okay, especially in the old times. That's how they implement, and everything's attached to the bus. For example, if you have a new devices and you want to connect it to the system that you want to do, so the architecture will look like, you have a central bus, right? And everything is connected to this with tri-state buffers. So everything, something like this. So if you have a new devices, you just put it in there. So it's very simple and very easy to expand, right? That's why they use the bus architecture, right? And this one, of course, the only thing is you don't have to worry about the collisions. It's always like determined. Okay, yeah. Okay, so that is the alternative, of course. But if you are using this, you can see that the way you control it, now you have to control what? Control these signals. Okay, let maybe give you another examples. What if you want to do the same things, the same trick, the same job? If you want to do R1 to R2, what do you want to do now? You can see the control signal now is different, right? Because of course, the algorithm is still the same. You have to move R2 to R3, R1 to R2, right? And R3 to R1. Okay, but the signal that you need to control is different. Okay, still same job. R3 to R1 first, then R2 to R1 to R2, right? And then followed by R3 to R1. Still the same. But the signal that to control this is different because what? What is the first one? What's the first one? Huh? Okay, how many signals that you need to control now? How many signals that you need to control now? Think about it. What do you have to do? You have to release what? Release R3, right? And what? Release R3 and what? And sorry, release R2 and R3 accepted, right? So how can you do that at the same times? Okay, first, how can you release R2 back to the bus? How? Now you have two control signals. You don't have, it's different, right? Okay, the control signal before you have six signal, right? Now you say that this is the control signals. Okay, but if you use the max, what's the difference? Now you have three signals to control. Now you have three signals. What is it? You have to control the max, right? The control signal will be S1 and S0. This to control the max, right? And what? And what? R in 1, R in 2. Because the release signal is no more. It's controlled by the max. And the output always present. It's just that you want which one you want to select out, right? Okay, and you have R in 0, R in 1, R in 2. Okay, let me draw this way so you're not confused. So now you have S1, S0, this to control the release, right? And then you have R in, R1 in, R2 in, R3 in. That have only, right? So the first step, you need to release what? To release R3 to R1. So what do you want? Release R3. How do you release R3? R3 is actually present by what? R3 is here, right? R1, R2, R3. Yeah, unfortunately, R3 is port 2, right? If you look at this is port 0, 1, 2, 3. So R3 is here, port 2. Port 2 is mean that S1 and S2 is 1, 0, right? 1, 0, we select port 3, and so let this one goes, and we select this one out, right? Which is R3, and then what? And then tell sorry, not R2 to R3, right? The first step is R2 to R3, R1. Hey, R2 to R3, sorry. Has to R2 to R3, R1 to R2, and R3 to R1. Okay, so release R2, yeah, release R2. Release R2 is 0, 1. because R2 is connected to port 0 usually. Okay, is it? Oh, they have a data going inside from external. Sorry. Oh, this is what you asked. Oh, okay, I see. The data is here. Sorry. You can see the data from outside. Like I said before, you can add external device to there. So this data is actually come from outside. Okay, so you have to select things that can come from outside too. Okay, so they arrange it to be at port 0. That's fine. Okay, yeah. Okay. So this R1, right? This R1, R2, and R3. So this you assign it to data. Okay. Okay. So port 0 is data 0 from outside. Okay, and this is 1 0, 2 0, 3 0. Okay, so that's happened. Okay, so R2 is at port 2. So you need this one to be 1 0, 1 0, right? And tell what? Tell R3 to exhibit. So you have to activate R3 in to be 1. Why these are 2 are zeros? So these are set of control signals. That's the first step that you need to do. And then the second step, what? R1, R2. So you release R1. This R1 is this, right? And tell R2 to receive it. That's the second step. And then the third step is R3 release it. Okay, and then R1 accept it. Okay, so those are the type of control signal that you need to generate. Okay, but now it's not going to be simple as a chip registers. As you can see that the one is not just propagate, right? But you also have to compute S1, S0, and 1, 1. Okay, so if you start off with W, then each one will be a function of W for each case. Okay, for each case, and also the sequence, like what the sequence number is. If it's the first one, then how you going to get W? And of course, this is called what? The finite state machine. Have you learned that before? I don't remember. 206. No. Did you learn that? Yes, of course. Yeah. And this is particularly a type of what we call the finite state machine, right? For each passing clock edges, then you need to generate a sequence of signals that do this. Okay, that's why the control signal is always the nature of finite state machine. Okay. Okay. So now you understand the hardware levels. Why I have to explain this? Because it will closely connected to the VHDL that we talk about. So if you understand what the hardware that you are doing with, then you can write VHDL very easy because it's just follow directly from the hardware. Okay. So what is the first step? Actually, you need this type of schematics. You should have schematics in mind. So it's different from when you try to write the software, right? The software you can just keep writing. Nope, not VHDL. Yeah. The best, the most efficient way to do this is to have your floor plan already. Your floor plan is the schematic. It can be RTL level, like I say, like this diagram. Okay, then you just follow directly or implement directly from the schematics that you have. Okay, so I always tell the students you have 3 components to be able to be good at writing all this stuff. First, digital design knowledge. Why is that? Because it will give you this type of schematics where you can actually knows what to do. The second one, you need to understand the language. For example, if you want a register, how you going to write that and tell the software that, oh, this is registers. You have to follow a certain pattern. When you look at the pattern, then you understand right away that, oh, this is the hardware that you want to generate. You cannot just write anything, randomly. You can't. Okay. And the third one is actually understand the tools. Why is that? Because the tools different. When you want to use the tools from Altera's, okay, or you want to use the tools from Xilinx, you know, Virtuoso or what is it, Xilinx softwares. Yeah, even the same companies, they are different. You understand the tools, and sometimes you can control the tools, how it's going to generate hardware too. For example, in some design, you may want it to be as small as possible. You want to save it, save the area because you don't have much space. You can actually control that in the software by setting some flag, right? And when it optimizes, if you try to compress or try to have the minimal resource as possible, or let's say, I don't care about the resource, but I want to do as fast as possible. You can tell that too in the tools. And of course, usually it will blow up your hardware. Instead of just, for example, one, it may be both 10 times, but it's going to be 10 times faster too. Understand? So it's like a trade-off between what we call the area and the speed. Okay. So if you understand tools, then you can do that too. That's why if you want to be good at designer at this level, you need to understand these three things. Okay. And then you'll be good. Okay. Next, I'm going to explain a little bit of how you're going to follow this. Okay. You understand a little bit of this, right? Generate. Okay. Okay. I guess you haven't seen this generic before, right? The generic is what we call the compilation times. Because generic is like, what do you call it? Customized. Means that it will not be generate until you compile this one. If you compile this code, for example, you said generic n, and n is equal to 8. That's the number you give. So everything that is n will be replaced n by 8. So basically, you expanded it by 8. For example, if you use n here and for port r, you can see vector n minus 1. What is n? N is 8. So now you construct something like 7 down to 0. So now you have the actual part, but it's not going to be understandable until you compile it. And when you compile it, it will be hit this, right? So now you have 8-bit registers. But this is good because next time when you want to expand it, let's say for a 16-bit, you don't have to go and correct all the code. You just come here and change this to 16. Understand, right? So it's like very simple ways to to make the code scalable by thinking about this. Okay, so if n is 7, then everywhere that you see n here will be replaced by 8. So this becomes 7 down to 0 as well. Okay, so you can see that, for example, you can edit, you can expand the port input and output like very easily. Just replace it with the n. So we call the generic n. It's like a dummy number where you can put, and n can be used anywhere, even in here, right? If you understand what happened, okay. Next is, as you can see, this is the register, n-bit register, and n is anything that you want, okay. If you use 4 bits, right, and of course, n will be 3. If you quote it directly, for example, and next time you want to change it to 8-bit, you have to dive into the code and change from 3 to 7 everywhere, right? But this way is not going to be much easier by just replace it at the beginning and, recompile everything. And that will be okay. Okay, and you can see that on the RTL level, to generate and a 4-bit and 8-bit register is very simple. Okay. If you want to generate 1 bit, okay, for example, if you have this one bit, D and Q with the clock, okay, with the clock, this is 1 flip-flop, right? 1 flip-flop, okay. You can say Q and R is the input with the clock, right, with the clock, and Q is the output, okay, output to Q, okay. That's 1 bit, for example, that's 1 bit. Okay, but if you have 8 bits, you don't have to write, for example, 0 out to Q0, right? Basically, you have to write this 8 times. Q7, Q7, get R7, Q6, get R6, and go on to Q0, get R0. Right? This is how you write it. It's the same things, right? But in RTL, you don't have to do this, right? You just write R assigned to Q and understand. So it's the same thing. That's why the VHDL is very convenient, because you don't have to specify the details. You just say that, okay, I assign the whole thing, right? Assign the whole thing, okay? But the catch is it has to be the same directions. What does it mean? It means that they're going to match 7 to 7. So this has to follow the same path, 7 down to 7. Okay. But what happens if you declare Q from 0 to 7? It's going to give you errors. Say that it's type mismatch because one is count from 7 to 0. When you write this, it means that R7 is the MSB. And 0 is the LSB, right? But if you write 7 to 0, it's going to be on the different side, right? This Q0 and Q7. That's why you cannot match it, okay? But if you want to really do it, what happened? If you want to actually assign this one to like Q7 to R0, what you going to do? Yeah, you have to spread this out. That's right. You understand now? Right? Okay. For example, if you want Q7 to get R0, then you have to write this one in detail. You have no choice. You have to write this one to R0 and Q6 get R1. You have to write it out. But if you don't write it out, it means that you are matching like 1 by 1, but it has to be same type or follow the same type. Okay, but it's very easy, right? Because then you don't have to do anything and you don't have to correct. Why is that? Because if one day you expand it from 8 to 16, then you have to come in and, writing more lines. Understand? That's why the VHDL is very convenient, because now you don't have to go and dive in everything. You just change here and it will be done very easily. Okay. Okay. And you have to understand, for example, this pattern will get you flip-flop, the flip-flop. Okay. Flip-flop with what? With enable RIN. You can see that everything is under the clock, right? Wait until clock event, clock. This one way to write it. What is clock event and clock 1? This is rising edge. Same as rising edge of clock, which is another, what we call the function in VHDL. This is the built-in function. We call rising edge clock underscore edge clock. Same, equivalently, this one. Okay. Why? Because they don't want to write that too long anyway. What is the meaning of clock event? Clock events mean that something's happened. Event means a flag, means that something happened to the clock, right? And clock equal to 1 means that after the event happened, clock equal to 1, right? Before that, nothing's happened, and then it's happened, and clock equal to 1. This means that before that must be 0. That's why it's rising edge. Okay, and what is falling edge? Falling edge is clock even and clock 0. Then it's going to be falling edge. Okay, because after it happened, clock equal to 0, which means that before that it has to be 1. And that's why it's falling edge. Okay, yeah. And if RIN under the clock, you can see that once you see the clock, you check the input signals. What is the input signal here? RIN. If RIN 1, then you transfer the data, right? So RIN is like the enable signal, right? So if RIN 0, what happened? Yeah, as you can see, it doesn't tell you, right, that what to do when RIN is not 1. It says that if RIN is 1, then you transfer R to Q. Okay, but what happened if RIN is not 1? What happened? This is the basic idea of VHDL2. What happened? What do you think? What happened? Huh? What's the meaning of don't do anything? You memory, you do the same. You memorize what you already did. And that's why it implement flip-flop, because flip-flop remember things. Understand? Right? Same as, you know, when you want to use if, else, or whatever, but you don't, what do you call it? You not completely define what to do in some of the states. Like I said before, if one, let's say if are in one, then do this. And else if are in zero, do something. What do you think is what you get? Okay, let's say I have the first part. If are in one, then do something. And then else if are in zero, then do something. And if. Is this a max? What do you think? Is a max? One do something and zero do something? What do you expect that? A max, right? You're not so sure. You're right. Well, on the logic level, of course, it's a max. One do something, zero do something, right? But it's not logic levels. It's lower than logic levels, like I said, because you are implementing something, some circuit. So what happens if it's stuck between 0 and 1? Oops. Huh? You don't know what to do, right? So in that case, what do you get? Huh? You get a memory, of course. If there's no clock, you get a latch. You remember a latch, a synchronous latch, right? You get a memory. But if you have a clock, then you still get a latch anyway. That's why instead of writing this, what's the best way to do this? You like else. Why? Because else means you cover everything. That is not one. Understand? Right? Because it can be any state now. It can be 1, it can be 0, it can be X undetermined, it can be high impedance. Well, you tell them what one do, what you do with when this is 1 and what you do with 0. But what happens when this is high impedance? Uh-oh. Understand, right? Okay, that's why you cannot use your mentality when you write a software on VHDL. You have to understand. That's why I'm saying that you need to understand the language. That if you're missing something, then you surely you get a latch. I used to do with students. They write this kind of code in the software styles. You can say that lots of like nested if and else. Oh, I think about like 10 times. And what happened with that? They compiled it for 10 hours, right? And then at the end, they said not enough memories. Oh, what does it mean? Because everything you miss, it will generate a nested latch. Nested latch means you have a network of latch that try to do something. And you have 10 level deeps. Every layer that has it, it multiplies exponentially. That's why there are no memories. Understand? So you cannot just use that mentality when you write software. That's why I urge you to first understand what the language did in the first place. Just don't write anything. If you understand, you can ask me what happened when you do that. Okay. Okay, and you can see there's a certain pattern that you can write to implement, we call imply a hardware that you want. For example, if you want to imply a tri-state buffers, remember that you want these things, right? So now you have the schematics. For example, now you have the schematics. The next level is to implement each component through VHDL. Okay, we did that with the registers. But now, if you want a tri-state, or you want to narrate about tri-state, what we're gonna do? It's here. This is how you write the tri-state buffers. Tri-state buffers. They use tri-n, right? N is generic. Okay, why is that generic? If you don't need to generic, you have if it's a single tri-state buffers, this is going to be just ST logic, right? ST logic and ST logic, right? And this is just F equals Z when else X. Then that's 1 bit. That's 1 bit. Means that if you do this, you just get 1 bit. But what happens if you want to use 8 or 4 bit at the same times to generate 8 at once, right? First, like I said before, you need to spread this out into 8 lines, and each line for each bit, right? But you don't need to do that, okay? In here, okay? Yeah, and also you may what you call it? You may wonder what is the artist is. Did I explain that to you? What artist is mean? Did I tell you that before? So I can skip. Still remember what is it? Artist. What is artist? Is keyword. This is a keyword. You can use it, okay, but you cannot use it as a variables because it's a keyword. Okay, what does it mean? Well, you need to understand how to construct an array in here. Okay, for example, F has 8 bit, right? So F is actually consists of, if you write it out, 0, 0, 0, 0, 0, 0, 0, 0. If you write it out like this, what does it mean? It's the same as F is 0, 0, 0, 0, 0, 0, 0, 0. Same thing. Okay, so this is like in a word of strings, but this is write out as what you call an arrays. So this is like position number 1. This is F0, this is F1, F2. Oh, sorry, this is down 2, right? So down to this will be 7. Okay, sorry. Is it? Oh, no, it's okay. This is 0, 1, 2, and so on to F7. I'm not sure though. This may be F7. No. Should be F7, F6, F5, and go down to F0. Okay. Yeah, but anyway, you write as an array form. As an array form, okay, or you can write it as string form. String is, this is F7, right, and go down to F0. Depend on the directions, okay, and this is, I think, in array form, this is F7 to F0, F0 to F7, sorry, okay. What is the difficulties? Of course, if you have F0, one line is you got 0, right? Z, right? C is also the when E equal 1, else X, for example, okay. Yeah. What is the problems? Okay, the problem is, for example, if there's a 4 bit, you can write 0, 0, 0, 0. Oh, no, you can write Z, 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 4 bit. Z, 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 4 bits. That's fine, right? But what happens if you have more than 4 bits? One day you change your mind from 4 bits to 8 bits. What happened? What happened? You have to come in here and change this one to this. Right? Understand? Because now it's 8-bit. Understand? Right? You have to dig into the code and change F from 4 string of 4 into string of F everywhere in your code. Understand? Right? Understand? Right? Means you have to look where the expansion is, and you have to change the width of from 4Z into 8Z, because now you change 4, 3 down to 7 down to 0. Oh, now you have to dig into there, or it's gonna give you an error that, okay, not enough one, or time mismatch, because you have to go and everywhere you want to change it. Okay, this is a trick that you don't have to. Just use one word, others equals Z. Why you will do that? Well, it's come from this. That's the next step. Okay, 0, 0, 0. This is what we call the infer, or you can say imply positional language, which means that the first one always attached it to F0. The second digit will always attach to F1 and so on, right? But there's another way that you can imply this explicitly. Why? You just write this F0 get 0. What does it mean? This is that F of 0 gets string 0. 1 gets string of 1, 0. 2 gets string of 0. And so on to 7 gets string of 0. Understand? This explicit one. What is the things of explicit one? Why it's good? Because it's explicit, right? You can actually swap the players. Because now you are so clear about it. You can actually change this one. For example, we can do this. And to give you the same thing. Understand? Right? Okay? Understand? Right? Because now you can swap whatever. Because now you imply that, okay, at position 1, you get 0, 2, you get 0. So it's clear. That's why we say explicit. That's why we say explicit. Not implicit form, it's explicit form. Then what else? Okay, let's say if F is look like this, 0, 1, 0, 0, 1, 0. Let's say in 8 bits, okay, I just have 1, 1 here. What happened? Then do I have to write all this? For example, this position is 1. Okay, let's say assume that. So I get this one at position 7 or 6, right? 6 is get 1 and else is 0, right? So I still have to do this, right? Understand? Right? But then it's very convenient. That's why they invented the others. Then you can shorthand it to 1 at position 1 get 1 and others. That is not 1. Then get 0. Now understand now? So you don't have to write out a very long one. You just write this one. It means that you just define where you need a 1 and then the others is 0. Mean the rest. Others mean the rest of the explicit one. Understand? Okay? And they just exploit it. Because if everything is 0, then you just don't use this, right? You just write others equal to 0. What does it mean? Everything else, which means that every bit is zeros, right? Okay. So what's the good thing about this? The good thing is that others means that all the rest, which doesn't depend on the bit now. So if you write something like this, which means that every bit is that, basically that's what it's saying. So in this case, if you expand from 4 bits to 8 bits, you don't have to dive into the codes anymore. Understand? Because now others imply that, hey, every bit. So no matter what, 4 bit, 8 bits, it's understandable that all the rest will be 0. This is a technique that they use to, to use for, keep the simple codes that you don't need to dive into and change everything. Okay, that's a technique that you can use. Okay, but I need to explain what the others does first. Okay. Or you can reset it. For example, if you want to reset F equal to 0 all time, you can use techniques too. If reset is 1, then F others equal to 0. Then in that case, you don't need to dive into the code and expand all the 0, 4 bits to 8 bits everywhere. Understand? So you can use technique to reset everything too. Okay. First, the third one is the control one, the shift register one. Okay, so now we already got this component, right? Okay, so we already get these components. We already get this component. The third one is this, right? The control circuit. And they use this one to control number 3. So you have to implement this one. Okay, and you can see that from this, it's just directly just 3 shift registers. Okay, 3 bits of shift register. You need to write out the shift registers. Okay, and this is how you write out the chip registers. Once the clock here, yeah, remember the process one. The process implies the sequential commands, which mean that the sequence of the events that happen will be in orders. Okay, will be in orders. Okay, so if reset n equal to 0, then as you can see, this is the reset, right? So you need these techniques, others equal to 0. Why is that? Because when you change k from 4 to 8, then you don't need to dive into the code. Right? Or if you don't use technique, when you write 4 out, it's going to be this, right? But if you change your mind to 8, you have to come into the code and change this line to this, which is very, very tedious one. You have to follow every code that has it. That's why we use these techniques instead, okay? And you can also use techniques because now I plus 1, 3 get 2, 2 get 1, and 1 get 2. Here, you can see. Oops, sorry. Here, you can see that, right? This is they use what? Q3, right? This Q2 and this Q1. So Q3 go to what? 2D or Q2, and Q2 to Q1. So it's jump. This Q3 is D, right? So once the signal comes, D will jump to Q, which means that D is Q3. That's why Q3 is assigned to Q2. Oh, sorry, Q2 get Q3, right? This way, sorry. It's this way. Q3 get Q2. Sorry. Has to be this way. This Q1, Q2, and Q3. So Q3 get Q2, right? Q2 will jump to Q3, right? And Q1 get Q2. Basically, this is what the chip register does. Okay? Yeah. Yeah, this is how to implement it. So basically, this is gen bit, right? This is the jump for loops. Remember, for loops can be used only in process. Can be used only in process. You never see this outside process. No, right? So what is that? Is it just repeated this line? For example, K and K is 4. So it's like Q3 get Q2, Q2 get Q1, right? And Q1 get Q0. Oh, no, sorry. Just down to 2 only, right? That's it, these 2 lines, right? And the last line is Q1 get W, okay, together. This is by the loops, okay? The loop, nothing, generic. For the loop, it just, it's just copy. You can say that it's just generate the code. That's why we say that this type of code is like generic codes. It cannot be used until you compile it, because once you compile it, we will replace this line with this sequence. Understand? Right? Once you generate it, finish, and you go into VHDL, you will see this line instead. That's what happened. Okay. Okay. Next is to assemble it. You can see that first you need to understand how to create all these components, right? Next, assemble all these components into the circuits that we want. That's why you need this plan. This plan. Okay, this plan. You can view each unit as the IC, where you have the output connected to the input of this unit. For example, the output of R2 connected to the input of this tri-state buffer, for example, and the output of this tri-state buffer connected back to the bus, for example. That's why the floor plan, these things is very important, because once you understand and you create each component, then you assemble it according to the plan. Okay, so first you need to declare, like here you see, need to declare the component that you want to use. We call this the component. You can declare it underneath here under the entity, or you can collect them together and put it in the package like this. Yeah, like this. This one. Yeah, you can put in the package like this. If you plan to use it somewhere else, then you can put in the package, right? And once next time you just use component, for example, use package components, it will give you that one, okay? Or these things can be put underneath the entities before you, entities, and then this component, and then architecture. So it's going to be like between those stuff if you want to use them. Okay. So the components mean that you're going to use this one, or each one is like an IC. So basically, right? It's like an IC. And the input output is defined. For example, component is actually like an entities. So basically we have an IC, right? And this one called register N. This IC called register N, right? And it has R in and Q out, okay, and clock and R in. This is like you have an IC, okay, same as the other one. Next, you need to assemble them together, and they call swap. Swap is what? Swap is this floor plan, right? This hardware we call swap. The whole things, the whole page is swap. Okay, this floor plan. Okay, next the floor plan is swap. Okay, then yeah, and in the swap, as you can see, what's the input to the swap? The input to the swap is data, right? And reset N and W. This is from outside. Okay, so you can see that there's a block called swap. And of course, you need to control from outside is reset N and W, right? And so data from outside, you have a bus outside, right? We call this the bus outside. Bus Y, out, okay. And in is are in external, okay, swap. You can see we assemble it together by what? By using the IC. Because you have an IC called register N, and you see how many you need. In that floor plan, you need 3, right? You need 3 registers. We call this register 1, 2, 3, because they are the same type, register N. You need to give it a name, or else we don't know which register you are talking about, because they are the same type. If you say, oh, I want to connect register N, but they will say, which one? Right? So you have to give it a name. That's why we call this register 1. This is a name, label. So we label it. Okay. They're all of type register N, but you give it a name. You give it a name. Okay. And of course, the interface is look like this. They all look the same, right? They all look the same. Q and R. This is Q and this is R, and the clock and R in. So I write it there. Why? Because it's inside, right? It's inside. This is RQ. Sorry, this R and Q, R and Q. They look the same, right? With the clock and R in, same. They look the same. Okay. So first, you need to give it a name, right? Name, and then you need to name the connections. For example, the output of this now it's 8-bit, right? 4-bit or 8 bits, doesn't matter. And where is this one goes? The output go to what? Go to tri-state buffer. Remember that, right? This go to tri-state buffers, right? And then tri-state buffer go to the bus. This is how you generate it. Yeah, we'll finish after this. Yeah, you see, output of 1 go to the tri-state, input of the tri-state buffers, right? And output of tri-state buffers go to the bus. Okay, so you need to give it the connections, or you can say the wires, the name of the wires that you're going to use. Okay, so the wires is signals in VHDL, so you need to declare that in VHDL as the wires that you want to use, as you can see. So these are the wires that you need to connect between all this, and you name it, right? And you name what? R1, R2, and R3 is the bus, you know, or the signal that you want to connect. Okay, and you can see that the output is bus wise because it receives output from the bus. right? Each registers, if you look at it, right? The output, the input come from the bus. The input come from the bus. Here you can see the input come from the bus. Sorry. Yeah, the input come from the bus. This is the bus, right? Bus Y. So the input come from the bus, and the output goes to the tri-state buffers. Okay, and so you can see here the input from the bus. How do you know this is a bus? It comes from the components. You declare this component, right? So the first one will be R. The first one, the first position will be R, right? And the second one is R in and clock. And you can see that we control it from R in and clock. R in 1, right? And then clock. Okay, and the output here defined as R1. So you output to the Y is called R1. And you can see that this Y is R1 is actually what? Go into tri-state buffer 1. Okay, so if this is register 1, this is tri-state buffer 1, tri-N1. So you name it. You can see that we label it tri-state 2. Okay, that's why if you have this one, you just implement directly. It's very simple. Okay. Same here. The input from bus Y and the control is I in 1. This I in 1, right? And this I in 2 and I in 3 following. And the clock, the output here is name is R2, right? That's why you need to label this R2 and go back to the bus. Okay, and you can see the R2's output. R2 here is connected or plugged into tri-state R2. Okay, and the control is this one, right? And you see the output go back to the Y's. So you see that if you have a for plan, this is very easy because just label everything and just code directly. Understand? Okay. Yeah. Okay. Yeah. This is what we call implicit again. There's always the easy way and the hard way. Okay. Because here, the position is implied by the components that you declare. For example, the sequence will be R in clock and Q, right? So the signal has to match all this. For example, the first one must be AC logic between N1 down to 0. And the second one and the third signals must be SD logic. It has to match everything, match position. But what happens if I don't want to match? Again, you can just use the explicit one by just writing out, for example, port map, right? And then the first one, bus Y, right? Bus Y is what? Position of what? Position of R. So you can write this. R get bus Y. Understand, right? And what? R in get R in 1. Okay. Yeah, no problems here because these are dummy. You can use the same signals, no problems. Signal name because these are, you can say inside the components, but it will understand once you jump inside the components. So you can use the same name, doesn't matter. Okay. And the third one is clock, right? So clock get clock. Yeah, you see. And the third one is what? Q, right? Q get R1. That's what the actual meanings, right? This is the hard way. So basically, if you explicitly, again, you can change the position, doesn't matter, right? You can change the sequence here. You can write Q first, doesn't matter. Okay, so you don't have anything because it's explicitly state which one got which. Okay, yeah. And remember, if, yeah, you need to label it to differentiate between each component. Okay, yeah. The rest is, I guess, yeah, just this. This is like gates. We call this like a trivial gates because you need to compute something, so we can do this. Okay. Okay, understand? Now I hope you understand more about what the code is meanings. Okay. Okay. This is for the marks. This is for the marks. For the marks control, This for the marks, and this for the tri-state implementation. Yeah, the marks is this one, right? As I already told you before. Yeah, this is page 6. Page 6. Page 6. Page 6. Okay. Yeah, same, right? Tri-states, not tri-state register is the same. Yeah, and remember that these are what do you call it? Concurrent statement. This actually can be swapped. You can swap any lines. Doesn't matter because it's implied the actual hardware. So it doesn't matter if you want to change whatever line it is. Doesn't matter. Okay. Yeah, and also you need encoder. Why is that? Like I said before, you need to control S, right? Like I showed you before, S go to where? And S has 2 lines. Remember that S1 and S0, right? 1, 0, select 1 and the others. Okay. Yeah, you can see that. Again, if you're not sure, use others. Use others. Okay. Because others mean cover everything just to make sure. Or else, don't use else if and else if, always close with else. Always close with else. Yeah, and you will be okay. Okay, yeah, let's take a break here, maybe for about 10 minutes. Oh, 3:30 is already. All right, so I come back later on. You have to go to the okay, let's come back next time. These times, yeah, because there's so details about it. I explained it a lot compared to the previous years, but I hope it's going to help you more to understand the fundamentals of all these things that you're going to do. Okay. The next example is that assume that you are going to design a CPU. Okay, this CPU has limited function. Okay, we say limited function. And number 2 is limited resource. Okay, yeah, you guys may think that, okay, resource not, what do you call it? Not a big problem, but before that, it's a very big problem. For example, what happened to you now if you run your computer, it's slow, you don't have enough memory, what do you do? Buy more memories, no problems, right? But before that, you don't have that luxuries. If you have, like, let's say, for example, like 3 registers, then you have to do with 3 registers. But you have to think about a way to do that. Okay. For example, in the old time, we use computers, we use the floppy disk. You don't have, what do you call it? You don't have the hard drive, and you don't have that much memory. So what you do? You have to move things around. For example, the first floppy is the OS to run it. and then you take the OS out, you put the data disk in, and then you run the function, right? And pull the data in to the memories. And if you don't have enough, then you need another disk to store temporary. So you have to think about this, how to move things around. You don't have the luxuries anymore. But here, well, is it too slow? Just buy new computers. You have to do. So that's why sometimes it's problems of management that you guys have problems with. Okay, but let's assume that we have limited functions for the stuff that we're gonna do. We want to design the simple processors, and okay, what is this processor has? First, it can do just these 4 functions. These 4 functions are, number one, load. Load is mean get data from outside. That's the first operations. We call operations, limited functions. The second one is move. You can move data from a register to another registers. Okay, that's the second function it can do. The third function is that it can add 2 numbers in registers, but what's the catch? The catch is after you add it, you store back in RX. As you can see, the function performed, the actual details is this. Okay, this is like what we call the mnemonic language. So you have what you're doing using just a simple symbols to identify. For example, data move data to RX, we just write an arrow for that. Okay, and number 4 is subtraction. You can do just subtraction between this Rx minus Ry and then Rx. Okay, but of course there's more detail on that. Okay, to describe the operations of register of a computer or of any CPU, actually there are three levels. Okay, the first, let's say that the first levels, the highest level, this is highest level, or the high level language. These are what? For example, like what? Python, C language. These are Python, C language, whatever it is. These are what we call the high levels. Okay. Of course. Oops. Okay. Yeah. Python, C. It has complexities, right? They are complex. It has the highest level, highest complexity, of course, but it can do a lot of things, right? It can do a lot of things. The second level is what we call the assembly language. So any high language will be translated into assembly language. For example, it starts off with command. We say command. The language is divided into 2 parts. The first one is what we call command, or the order of what to do. Okay, and then followed by the argument or the data that you need to work on. Okay, so it consists of 2 parts. For example, like this one, you can say this assembly language. So it's tell you what to do. For example, load. What is load? What is move? What is add? Sub. Usually it will give you just a short name. For example, sub, they use sub, you know, or subtract, for example, or multiply, they use mul, MUL, to make it like shorten. Okay. And of course, depends on the computer. Did I tell you about RISC or CISC before? No, right? Yeah, we're gonna talk about that later on, where we have 2 types of computer. One we call RISC and the other called CISC. So the command will define what do you call it, the capability of the computer that you can do. Of course, some can do multiplier, some cannot, depends on the hardware that it has. So the number of commands is very important. Numbers of things that it can do that can be done on this computer, that can be done on this computer. Okay. For example, this one can do just 4, right? But for the actual CPU, it can do like 100 of jobs. You have 100 commands, for example, right? For the RISC one, it has only like 30, 40 commands. For the sys one, it has more than 200 commands. Why it's important? Of course, everything you need to code into commands, right? And then the arguments mean the resource that you can work on. What is this one? This is usually mean registers or the storage that you can work on, right? For example, you can have 20 registers, or you can have just 3 registers. Of course, implementation is different, right? And how many arguments? How many? 2. 2 arguments, 3 arguments. Usually it's going to be 2 to 3 arguments. 1 or 2 or 3, depends of the complexity. But as you can see that, so design a computer is it's like complicated because this thing need to be determined before you start. Okay. And the third one, for example, this is like load something, right? Load R3 with R1. Usually, if you separate by command, for example, like this. Okay, and the third level is what we call the machine language. Machine language. Did actually understand the command, the arguments? No, these things actually what? It's just a number. For example, if it's 8 bits, it means that the command is 8-bit commands. For example, you have an 8-bit commands. It's just a sequence of number. Example, right? This is what we call the machine language. It's just we call this mnemonic, right? Sometimes we call this mnemonic language. Mnemonic language. So it is like numeric language. So it's like number. It gives you a number 1011, and usually it's not clear unless you understand the structure of the commands. For example, if it has 2 or 4 bits, it can divide it. For example, this will define the commands, and this will define the arguments. For example, of course, the length of the command depends on, for example, the resources you have, right? And the command is, of course, the instruction. We call this the instruction, right? Command or instructions, or you say command or instructions. How many you have? For example, if you have 4 commands, okay, how many bits you need to identify? 2 bits. 2 bits enough, because now you can separate each command. For example, you can assign the load to be 00, 01, 1011. That's enough. When you see 00, the first bit, oh, I'm doing load. Or you are instructed to do load. I say 1 by, oh, you're going to do subtraction. So you understand. But you need to understand before that. That's what each code does, right? Everything is coded. You can say everything is coded. And the argument as well, because if you have 20 registers, for example, if you have 20 registers, so how many bits do you need to identify each registers? 5 bits, right? 2 to the 5 is 32, but 2 to the 4 is just 16. But if you have 20, then 4 bits is not enough to identify all of them, right? Understand, right? Then you need 5 bits to identify each registers. And if you have 3 arguments, what happens? For example, you can add R1 with R2 and store in R3, for example. If you have 8 R1 with R2 and store in R3, ooh, your command is like huge, right? Understand? Because it's a 5-bit, 5-bit, that's only 15 bits. So you understand the length of the command is depend on the resource that you have. That's why I'm saying that for this particular example, you have limited function and limited resource. Because now you have only what? 4 registers. You don't have that 20 registers, you have 4 registers. For how many identifiers or arguments bit you need for 4 registers? 2, just 2. So that's why the command is short. Understand? Okay. Yeah. So the total command is actually what? Just what? Just 6 bits. It's enough, right? 6 bits is enough because you have load data and blah blah blah, right? No, I think you have more. You have 4 registers and you have data. So you have 5 actually. So you need 3 bits for each performance. Well, it depends of how you want to define all this, okay? But you need to understand first the structure of the instruction, what it consists of, and you need to understand the code that actually identify what type of function. So you will see that it's like very cryptic. If I give you machine language, you'll be there. Usually these are the bin type. You see, when you load something and it's .bin or .exe, these are the type of machine language. Understand? So if you separate into pieces, you actually understand what it is. So it's been converted from assembly language into machine language. That's it. So this is like cryptic. So the next level is assembly language. At least you understand what it does, move, blah blah blah. But you may not understand the big picture. But at least you understand what it's doing. All right. Okay. For these types, as you can see, so you need 2 bits for this, right? And each argument, I think you need 3 bits because you have data as well, right? So this is 4 plus 1 data from outside. So you need 3 bits. So 8 bit is enough. This one, 8 bit command is enough. Okay, and we still have to imply a lot of things. For example, add. You don't use the third registers, right? You add these 2 together and then store back to the Rx. But as I say, if you say that, oh, I can add Rx to Ry and then store at Rz, oh, this is another one, right? Because now you need the third argument, which means that you lengthen the command. So they don't want to do that. So they have to keep things simple. That's why they limited some things to this. And you see the operation is actually depends on the hardware that you use to, right? Everything is slightly related, okay? Yeah. So these are operations can be worked by, but yeah, you're missing the minus sign here. These are the minus sign, right? On the slide, I think it's white, but it's actually minus, okay? Yeah, and before that, then you need to understand that you have 4 registers, right? And then you have adders. This is ALU. So you add sub, sometimes it's just called add sub. Add / sub. And I don't know if you still remember from 206, when you add and you minus some things, it can be done in what? In what type of what you call arithmetics? You have what? Sign magnitude and what? 1 complement, 2 complement. What are the most common ones that they do? Still remembers or already give back to the professors? Okay, what are you using? 2 complements. Why it's 2 complement? I think you already explained that, right? No? No? Oh, let's go back and refresh your memories if it's still there. Okay, when you want to add 2 numbers together, no problem, right? For example, 0, 0, 0, 1. Okay, so that is what come like this, right? This is unsigned. But if you have 2 complement numbers, the first one will be signed bit. So this is what we call overflow, because now the positive turn into negative numbers, right? So the 2 complement number has a range. Remember that? For example, if it's 4-bit, the first one will be divided as a sign bit, then the range will be what? From plus 2 to the n minus 1, right? Between this and minus 2 to the n. Yeah, minus 2 to the n. So the maximum, for example, the maximum is 7. The minimum one is minus 8 between this. Okay, and remember, let's say if we stay in cost, for example, it's 1001 and 0001, and you add in 2 complement numbers, you get 0110. No problems, right? This is plus 5. This is +1, so you get +6. Okay, yeah. And what happens if you do minus? You do 5 minus 1. So what do we actually do? We coded 5 and -1 into complement numbers, right? So what is 5 into complement number? It's positive, so it stays the same, right? It stays the same. But for -1, what happened? You need to convert the code into two complements number code. How do that? First, reverse to make it one complement by flipping all the bits. So you get 1 0 1 1 1 1 0 flip, right? And then what? +1 to make it change to complement. So you get 1 1 1 1. Okay, 1 1 1 1. So 1 1 1 is the code for -1, right? And then you can plug in here 1 1 1 1. Okay, then what? Then add them together, right? Directly. You can see that 1 1 is 0 plus 1 is 0 plus 1. 1 1 1 is you get 1 and flip this 1 1 1 is 0 1. So we are in the 4-bit two complement system, so this one doesn't count, right? But you can see that this one is positive and is +4, right? So the output will be +4 according to this. Okay. Understand? That's why we do stuff in two complements. Or let's say if you do -5 plus 1, yeah, what happened? You should get -4, right? So +1 is the same. Okay. What is -5? -5 is 0 1 0 1. This +5. You do one complement, that 1 0 1 0, right? And two complement, you +1, you get 1 0 1 1. Okay, so this is 1 0 1 1. And you just add them directly because -5 plus 1 is -4, right? You can try that. 1 1 is 0, 1 is 0, 1, right? And 1. It's not directly -4. It's the code for -4. It doesn't mean that you can separate this. If you want to do, you know that this is -1, right? Let's say +2. So it changed a little bit. So it's not the same. Let's say +2. So you should get -3, right? 1 0 is 1, 1 1 is 0 1. As you can see, -3, you cannot do this because you cannot separate this and do it as a sign magnitude. It's the code. So you have to decode it to get the actual values, right? How you can decode it? You flip it all over again and then +1. So you get 0 0 1 1, which is a +3, right? Which means that this code is actually -3. Okay, you need to decode it first to see its magnitude. Okay. As you can see, everything we do in two complements, right? But the trick is, as you can see, when you add them together as one bit here. So what we do is we do one full bit addition, right? Remember that you actually add it with what? With carry, right? With carry. So the first line is carry. For example, 1 1 0, you get 0 1, right? And 1 is the carry from the previous one. You got 1 0, right? Okay, this one is actually going to the other one and add them together. Remember that? And you get a 1 again, 1 0. So these zeros go up here, right? And add with the next one. Okay, yeah. When you do minus, if you still remember, we have a trick that we don't need to add them here. We can add it later on because if, for example, if you do 5 minus 1, you can actually spread into 3 lines. It's 0 0 1 plus 1 complement of -1, which is 1 1 1 0. This is 1 complement, right? And then you need +1, which is 0 0 1. We actually slip it into three space. Understand, right? And then so you add +5 with its one complement of number 1 first, and then add 1 later on. How can we introduce 1 later on? We can introduce it here as the carry. Understand? Right? So we can introduce the carry. So it's very easy, straightforward. If you addition, the carry will be 0. You see that? If you add 2 numbers together, then the number is 0. But if you want to subtract 5 with 1, right? You just enter here with 1. Here, then you get 5 minus 1. But if this is 0, then it's 5 plus 1. And you don't need to flip it. You just 0, 0, 0, 1. Okay, so that's why here we need to subtract here, yeah, and A and B can do simple stuff. Okay, so that's how you explain it, that you can do this. Yeah, we run out of times, and of course, except then 3, 4 registers you can work on. You can see that in the add sub, you also need the extra one we call A and G, and these are not what we call the universal registers. These are universal registers. Why is that? It's the storage open that you can use by anyone, right? By anyone. But A and G is only for what? For the ALU. This is the ALU, right? For the add sub units. Why do you need A and G? Why? You have any idea? Everything is explainable in the hardware. And of course, you will do this too once you design. If you get less experience, why you need A here? You know why you need A here? Because when you try to add 2 numbers together, let's say if you want to add R0 and R1 together, you cannot bring both at the same times because you have just 1 bus. You understand? First step, you need to bring R0. For example, you need to bring R0 to A first, store there temporarily, and then bring R1 later on, B, and then add them together. Because you cannot bring them together, you have 1 bus only. So you can carry just 1 data at a time. That's why you need to temporarily store it first at A. Okay, understand? That's the reasons why you need A there. And of course, you can have a choice of having B2, right? You can add a storage at B2, right? But to save the resource, what happened? Let's say, think about it. What happened if you have a register at B2? What happened? What happened? You need extra clock cycles to store B first. Because if you don't have this storage B, you can just bring in the data directly from add sub. Okay, and if you do that, when you add them together, once the result finish, why you need G? Why do you need G? Do you have any idea? Because these are combinational units. So what does it mean? Combination means you cannot stop. Once the output is released, let's consider if you don't have G, the output will come out, right? And go back there. What happened? What happened? It will collide with the data set enter B, right? That's why you need to store it first. Don't go messed up with that, or your result will be crashing over again many times. That's why you need G here. What? To store temporarily first and then move it later on once the bus is free. You see that also the disadvantage of having a tri-state buffer too. You can move just 1 at a time. You cannot move more than 1 at a time. Okay, but you save the space by just using this. Okay, but you need to think more carefully. Okay. Yeah, actually, yeah, like I said before, you can actually do this too, right? Yeah, if I put B here, if I put a B here, then I don't need this. Why? Why? Because if I put it here, right? Once I load R0 here, R1 here, then the bus is free. So in this case, I can let the data out and go to store it at any place I want because the bus is not used anymore, right? Understand? Right? Because if you put register here, then the first cycle you load R0, the first cycle you load R1. Then you have both operators, operands, right? Then when the output come out, then the bus is free because now the bus is not used anymore. Then you don't need G at the output. You see, that's the choice of what you need. And once you change it, then the algorithm will be changed and the signal control will be changed. Okay, so this is the option. Okay, understand? All right? Okay. You see, so now we bring in the add sub by, you see that the add sub is mean that if you want to add, it's 0. If you want to sub, this one will be 1. If it's 1, it's add sub, is it sub, then this one will be 1. Means that you are adding what? The one that need for the to complement in the first bit here, right? Here. You introduce it here. That's the first bit that you introduce. If it's add, then it's 0, right? And if you subtract, this one need to be 1. Okay. And then for subtraction, I think you need an inverse here. Do they have the inverse here too as well? Yeah. Okay. Anyway. That's the step to perform and with the hardware choice, like I said before. Next, I'm going to tell you a little bit of course, this is the level that you see, right? But on the bit level, it has to do many cases. For example, like this. T1, this is the edges. For example, you want to load, like I said, now your command has what? 4 commands. So your instruction needs only 2 bits. The first 2 bits is instruction. For example, load maybe 0, 0 for the first 2 bits, and then 0, 1, 1, 0, and 1, 1. Okay. Then the argument, the external one, and so you need 3 bits each, right? So I guess it's divided into 3 bits. Okay. So load, you bring the data from external. Here is the external one. Okay, you bring the data from external, go in there to any registers. Okay. Yeah. X is any registers. Okay, so you bring in there. Okay, and then it's done. So you can just complete in 1 cycles, right? Mean that you activate external. Yeah, you activate the external here. Yes, that external. Control the external. Yeah, here. That's external. So you activate this. So you let the data from outside get in, right? And it's go to every place on the bus. Okay. For example, if you want to store in R0, you just get this argument to be 0, 0, 0. What is it? Yeah, you let this one to be external. It can be 0, 0, 0. And this one can be 0, 0, 1, for example. Understand? So 0, 0 means external one, right? And then 0, 0, 1, for example. Yeah, and then you're done. So this can be completed because you activate these 2 signals at the same times. External is 1 and in equal 1, right? And so the data is actually going here already. So you just activate this one, right? And the data go in right to this one, and when the clock comes, this one will jump in there. Okay, so you just need 1 clock cycles. Okay, but for other commands, you may need more than 1 clock cycles. For example, if you want to add, you can see if you want to add, you have to think that the sub, like operations that you need to do, right? First, you have to move the R1 to what? To X. R1 of X. For example, first step, you need to move, for example, R0. Let's say add R0, R1. this command very easy, right? Once you see 0, 1, it's add. Then you look at the next 3 bits and you see 0, 0, 0 here. 0, 0, 1 and 0, 0, whatever. Okay. This must be 1 and 2, right? So 0. Okay. R1 to R2. Okay. Then what happened? It's the first step. You have to move R1 to this first step. The first step, move R1 to A, right? Move R1 to A first, right? And then the second step, move R2 to B, to enter at B. Then what? Wait for the clock signals, right? The result will come out at G, so it will store at G, store G. Then what? Then move G to what? G back to R1, G back to R1. You can see the step here. So you actually have to do sub steps in order to complete this command. Just one command, but you have to do several steps. It's not just simple command. So you actually need three steps to do this. First, you see that X is any, for example, like R1, right? You release R1 and store A in, activate A in. And so when the clock comes, then R1 will go into A. So now R1 is in A, right? Already. Okay. And then you release B, right? This is B, so it's R2. And G in. G in. So you once R1 plus R2 already, right? It already come out, right? And it will be stay at the entrance of G, but not in yet. And at the same time, you need to provide them with the N sub equal to 0, which means that you're adding up. So once the clock came in, then the result will be stored in here already, right? And then you move it back by, this one is R in or a 0, right? R in 1 is 1, right? And then done. Done is you wait for this. Done means, hey, I'm ready. I'm finished for this command. You can see you need 3 clock cycles, not just 1. Okay, so each command can have different length. And this is what happened to SIS computer. I'm going to talk about that. We call the complex instruction register. And as you can see, the more difficult commands can last like 100 clock cycles. Like what? Like multiplications. Of course, on the paper it's easy. Multiply everything. But what happened in the actual algorithms? What happened to the actual algorithms? You need to add, to multiply and add, and then keep adding until you reach that limit. Understand? Right? So it can last 100 clock cycles just from one single command. Understand? Right? Unless you have a specific hardware that can multiply 2 numbers in 1 clock cycles, then you can of course do in 1 clock cycles. But for general CPU, they don't provide that because it's expensive, and you need like areas to do that, because multiply is not small, it's big. Right? That's why in the old days you cannot do that. Okay, only for we call the scientific processors, then you can do all this stuff. In a more advanced one, in like the old workstation, you can even do square root with hardware. They generate special hardware to do square root in the old time. So the workstation can perform something really quick. So they call it like scientific processors. So you can do like exponential in just 1 clock cycle because they have hardware to do it. Understand, right? It's very complicated, but it's very big one, but it can do in 1 clock cycle. Or else you have to break into steps like this, right? And then take each step. So it can last like 100 clock cycles. And that's the beginning of the arguments between RISC and CISC, which I'm going to tell you maybe next time, okay? In the last one chapter. Okay, so let's finish for today. Next time, I'm going to explain you what happened next, okay? Sorry. for going a little bit over because we start pretty late. So yeah, and next time I'm gonna give you the oh, okay, hold on. I have to make the arrangement for the extra lectures because we will have 2 holidays, 7 and 14. We'll miss that. So what is the best time? Or we're gonna discuss that in line group? I don't know. Of course, next week is holiday, right? Monday the 7th is holiday. So we don't have class. And also on the 14th, which is Songkran Festival, we also don't have. So we missed 2 class, which is 6 hours. So I guess I have to make up at least 1 class. Okay, 1 class for that. So what's the best time for you guys? Friday? Any suggestion from online? Everyone make up, right? I guess. Huh? In the line group? Okay. At least for sure, in Songkran holidays, we miss the whole week, right? Half of the week. Monday, Tuesday, and Wednesday is not available too. So we only available from 17 and 18, which is Thursday and Friday. Yeah, I don't want to disturb you guys during the holidays. Are you guys okay? I don't think so, right? 7, 8, 9. So Friday is not. Actually, I'm quite what do you call empty. I'm available most of the times because my my teaching load is almost gone for other subjects, so I can actually do almost any time that you want. So what will be the best one? I don't know. Okay, or maybe let's vote. I don't know. Yeah, but yeah, for the backup class, I'm gonna record it for sure. Yeah, because most of, like you said, like most people may not have the same times, right? So it's better, but try to accommodate as much as many people as possible. Yes. Okay, so that's it. Everyone's left.
Wait, Professor, I have a question.
Yes.
So, in the assignment 3, that's due in like 2 days.
Yes.
One of the deliverables say that we have to do like a video demonstration. Like what does that entail?
Okay. Let me see the assignment. I don't remember. It's Professor Sri's assignment, right?
I'm not sure. I think so. Yes.
Okay. Let's see. Assignments 3. Where's that? Assignment 3. Ah, okay. Professor Sri's. อ๋อครับเชิญเลยครับพอดีคุย Oh, explain what you're doing.
No,
right?
no, that's the test bench example. The assignment is in the other link.
Okay. Is it in assignments? Where is that then?
It's in assignment. It's in that assignment, but it's on the other link next to
okay,
the test
okay.
bench.
Okay. Playlist?
It's
okay.
the link to assignment.
Okay, I
yeah.
see that. I see that. Sorry. Okay. Oh, explain what you do, I guess, to get the results that you have, because you write it out, right? You have to demonstrate what you do in order to get the results that you want, that you have.
Yeah, but I figured there's already like a discussion on the results and the design. So do we just repeat that in like a video format?
Yeah, I guess so. Because
Okay.
yeah, the professor just want to see if you actually do the work.
Okay, okay.
Right? Okay. You're not copying from someone. So you should have your own codes. Yeah. You understand what you are doing, right? Because if you don't do or don't code by yourself, I don't think you can explain that very well. Right? Okay. Hello? Okay.
Yes, yes, I understand now. Thank you.
Yeah. You're welcome. And stay safe. You are in Pattaya, right?
No, that's Lara. I'm coming. I'm a
it's
different
me,
person.
okay.
Yeah.
Okay, sorry.
Different people, Prof.
Oh,
Different
sorry,
people.
sorry. Okay. All right. So everyone stay safe. And yeah, let's meet you next time, I guess, after Songkran Festival. Okay. Yeah, I'm going to stop that because now it's already time. Okay.
Thank you. Bye.
You're welcome. Bye-bye.